So, till now we had dwelt with essentially the rectangular coordinate system, the eigenfunctions in the rectangular waveguide, we covered that, and we had a detailed study of the rectangular waveguide. So, now we are going to investigate the cylindrical waveguide or the circular waveguide, that is more popularly called, and the circular cavity, but before that we have to have a general idea of the cylindrical wave functions that are used to describe the wave behavior in the circular waveguide domain. So, the characteristics of the cylindrical wave functions, the types of cylindrical wave functions that are used, their properties. So, all of them needs to be carefully studied in order to like choose the appropriate wave functions for the cylindrical coordinate system. So, let us go to the lecture on this. So, these are the cylindrical wave functions. So, just like in the planar domain or in the rectangular domain, we began with the Helmholtz equation, the solution to the Helmholtz equation, or so appropriate to say the source free Helmholtz equation or the wave equation gives rise to the eigenfunctions in the rectangular coordinate domain, and then the eigenvalues are appropriately chosen in order to satisfy the given boundary conditions in the rectangular coordinate system. In a similar way, we will start with the scalar Helmholtz equation in the cylindrical coordinate system. So, the scalar Helmholtz equation in the cylindrical coordinates reads as follows: grad square plus k square psi equal to 0. And then we have to express grad square psi in the cylindrical coordinate system. So, that is what exactly we proceed to do. So, grad square psi is actually given by 1 by h 1 h 2 h 3 del del u h 2 h 3 by h 1 del psi del u plus del del v h 3 h 3 h 1 by h 2 del psi del v plus del del w h 1 h 2 by h 3 del psi del w. So, where h 1 is 1, h 2 is rho of the cylindrical coordinate system, h 3 is equal to 1 and u equal to rho, v equal to phi and w is z. So, rho phi z being the coordinates of the cylindrical system. So, we are all familiar with the cylindrical system. So, if this is a cylinder, so this is the z axis, this is the rho direction, and this is the azimuthal direction phi. Okay. So, we are all familiar with this cylindrical coordinate system. So, now what we do is that substituting these values, we get grad square psi equal to 1 by rho del rho of rho del psi del rho. So, all we are doing, we are substituting H 1, H 2, H 3, U V W in the previous equation for grad square psi plus del phi of 1 by rho del psi del phi plus del z of rho del psi del z. So, that is equal to 1 by rho del rho rho del psi del rho plus 1 by rho square del square psi del phi square plus del square psi del z square. That is pretty much simple to understand. So, now from the equation grad square plus k square psi equal to 0 or the source free Helmholtz equation, we can write this as, that will imply 1 by rho del rho rho del psi del rho plus 1 by rho square del square psi del phi square plus del square psi del z square plus k square psi equal to 0. So, this is the Helmholtz equation in the cylindrical coordinate system, which we will try to solve using the separation of variables, which is the same technique applied for the finding the relationship between the wave numbers and solving the rectangular, the Helmholtz equation in the rectangular coordinate system. So, following the method of the separation of variables, following the approach of the separation of variables, we let psi is equal to, so we let psi is equal to r rho. So, psi phi and capital Z small z. So, we break up psi into 3 distinct functions. One is r, which is a function of rho only, big phi a function of phi only, and capital Z, which is a function of z only. So, this is the distinct decomposition of psi. So, we call this equation 2. Now, all we have to do is substitute 2 into 1, because that was the purpose. We broke up psi into distinct functions of r, capital Phi or big phi and capital Z. So, substituting 2 into 1 and dividing by psi, we finally get 1 by rho r d rho of rho dr d rho plus 1 by rho square a capital phi d square capital phi d phi square. Note that this is the small phi. So, capital phi, which is a function exclusively of small phi, is we are finding the double derivative of capital phi with respect to small phi, plus 1 by capital Z d square Z d Z square plus k square equal to 0. So, again this is capital Z, which is a function exclusively of this small z, and that is capital Z double differentiation of capital Z with respect to small z. So, now we call this equation 3. So, we note that the third term, which is this, it is independent of rho and phi. It is independent of rho and phi. Okay. So, this is independent of, we see that this is independent of it is a function only of small z, because capital Z is a function of small z only. So, therefore, it must also be independent of z if this equation has to sum up to 0 for all rho, phi and z. I repeat that once again, because this term is independent of rho and phi. Okay. So, this must also be independent of z if equation number 3 is to hold good and the left hand side is going to or sums up to 0, the left hand side sums up to 0 for all rho, phi and z. So, therefore, we can write 1 by z d square z d z square can be written as minus k z square. This is 4, where this is a constant. Okay. So, where k z is a constant. Now, we substitute 4 into 3 and multiply by rho square. We substitute 4 into 3 and multiply by rho square. If we do that, we will obtain this equation, rho by r d d rho, rho dr d rho plus 1 by capital phi d square phi d phi square plus k square minus kz square rho square equal to 0. We call this equation 5. Now we note that the second term is independent of rho and z, and the other terms are independent of phi. So, this is independent of rho and z, and the other terms are independent of phi, and therefore 1 by capital phi d square phi or d square capital phi d phi square must be equal to minus n square, again where n is a constant, because otherwise the right hand side cannot add up to 0, or sorry, the left hand side cannot add up to 0. So, we call this equation 6. Using equation 6, 5 can now be written as rho by r d d rho of rho dr d rho minus n square plus k square minus kz square rho square equal to 0. Plain and simple algebra. Call this equation 7, which is an equation in rho only. So, this is a equation in rho only, there is no phi, there is no z. So, we write this is an equation in rho only. So, thus the wave equation is separated. So, thus the wave equation or the Helmholtz equation, the source free Helmholtz equation, is now separated, and we can define k rho square plus kz square as k square. So, we define k rho, sorry, we define k rho as k rho square plus kz square is k square. We call this equation number 8. After we do this, we write the separated equations 4, 6 and 7 as we write the separated equations 4, 6 and 7 as rho d rho, rho dr d rho plus k rho square minus n square times r equal to 0. Okay, that is equation 7, rewritten we call that equation 9. And d square capital phi d phi square plus n square capital phi equal to 0, that comes from equation 6. So, we call this equation number 10. And we also write d square capital Z dz square plus kz square z equal to 0, that comes from equation number 4. We call this equation number 11. Now, we note that equation number 10 and 11 dealing with capital phi and capital Z, they are harmonic equations, and therefore, they would be satisfied by harmonic functions. These harmonic functions we generally denote by h n phi and h k z z. So, h n phi would satisfy equation number 10 and h k z z is going to satisfy equation number 11. The R equation, this equation is Bessel's equations of order n, solutions of which can be denoted by the term B So, the R equation is Bessel's equation of order n. So, this is the R equation. This is the R equation which is Bessel's equation of order n, and the solutions will be denoted in general by B n k rho rho. So, we will denote the solutions to equation 9 by B n k rho rho. So, these will be generic solutions to equation number 9. Now, commonly used solution to Bessel's equation are, let us write down the common solutions to the Bessel's equation. B n k rho rho. It can take the form of J n k rho rho, which is the Bessel function of the first kind, or n n k rho rho, which is the Bessel function of the nth order of the second kind. It can take the form of h n 1 k rho rho, which is the Henkel function of the nth order of the first kind, and Hn 2 k rho rho, which is the Henkel function of the second kind. So, where we write Jn k rho rho is the Bessel function of the first kind, as we said, Nn k rho rho is the Bessel function of the second kind, Hn 1 k rho rho is the Henkel function of the first kind, and Hn 2 k rho rho is the Henkel function of the second kind. So, according to the equation 2, where we wrote psi as a combination of three distinct functions of rho, phi and z, we can now write the same equation or the same solution in this form, which is phi k rho n k z equal to Bn k rho rho H n phi and H k z z, which we call equation number 12. So, these form the solutions to the Helmholtz equation in the cylindrical coordinate system. So, as a product of the two harmonic functions H n phi and H k z z, in addition with this function Bn k rho rho, which can take all these different forms. So, which form it will take, which form the function Bn k rho rho will take, will depend on which region we are interested in to describe the fields in the cylindrical coordinate system. Does the region include the point rho is equal to infinity? Does it include the point rho equal to 0? Does it refer to any other kind of boundaries which are characteristic of any cylindrical region, like a dielectric boundary or a metallic boundary? So, based on these factors, the form of Bn k rho rho is going to be decided, whether it is going to be either of these four forms. In addition, we must remember that k rho and k z, this k rho and k z, they are interrelated by equation number 8. So, they are interrelated by this equation, which is k rho square plus k z square equal to k square, which we had called equation number 8 previously. So, we call this psi elementary wave functions. So, these are called elementary wave functions. Now, we must also remember that linear combinations of Bn, Hn we must remember that linear combinations linear combinations of the elementary wave functions are also solutions to Helmholtz equation. Okay. So, we can sum over possible values of n and k rho, just like in the rectangular coordinate system we sum up over the values of k x, k y, like that. Like in the rectangular waveguide we saw that we sum up over the values of m and n from 0 to infinity. Okay. So, here also we can sum up over the possible values or eigen values of n and k rho or n and k z, but we cannot sum up over k rho and k z because they are interrelated. So, we can sum up over these two eigen numbers or eigen values, or we can sum up over these two eigen values, but we cannot sum up over k rho and k z because they are interrelated. For example, we can write psi as sigma n k z. So, we sum up over the values of n and k z, C n k z psi k rho n k z. That can be written as summation over n and k z, C n k z B n k rho rho H n phi H k z z, which is equation 13. Okay, so, we have summed up over n and k z to express the total psi as a summation over these modes, the azimuthal modes, so to say n, okay, and over k z, where the C n k z are constants. So, these are constants and this psi is going to satisfy Helmholtz equation. So, let us stop here, we will continue from here.